In this video lesson, we're going to focus on graphing exponential growth. So all exponential functions, again, are going to be of the form y equals a times b to the x. So there's going to be two types of exponential functions, what's called exponential growth and exponential decay. So exponential growth is any time our b value, which again is our multiplier, is going to be a value greater than 1. So for example, if I gave you y equals 2 times 3 to the x, here my a value, which is again my initial value in my function, b is my multiplier. In this case, my multiplier is 3. So since b is bigger than 1, here's what is going to happen. I would start off again with the number 2, and that multiplier of 3 is going to explain how many times I'm multiplying by 3. So if I multiply by 3 once, let's say that x value, that input was 1, multiplying by 3 once, that would give me 6. If I were to multiply that 6 by 3, so say my exponent was 2, that would give me 18. If I were to multiply 18 by 3 again, it's going to give me a value of 54. So as you notice, if I take a look at my initial value and then track my values every time I multiply by 3, you'll see that the values are getting bigger. So this is known as exponential growth, and it occurs anytime the b value is greater than 1. So our focus for today is going to be primarily on graphing exponential growth functions. So in each case, you're going to be given your function of y equals a times b to the x. So we're going to first identify what are a and b. In this first example, we're going to use a table of values and plot some points to see what the exponential growth function looks like. And our hope is to then possibly find maybe a shortcut on how to graph. So in this function, y equals 4 times 4 to the x, my a value is going to be the 4, and my b value is also going to be 4, but inside the parentheses. So let me just jot this down. My a is 4, and my b is 4. So what that means is I'm going to start off with a value of 4, and the multiplier of 4 is going to give us what is going to happen to that initial value. Now what we're going to do is, instead of just taking the value of 4 and multiplying it over and over again, we're going to make a table of values and see what these points look like, not only on the positive side of my graph, but also what it's going to look like on the negative side. So in order to graph this function as well as any function, we're going to have to choose some inputs. Our inputs, again, are always our x values. We're going to use our function to plug those values in for x and evaluate and get our outputs. So what I'm going to do is I'm going to choose inputs based on my graph. So my graph goes all the way from -6 to 6. When I choose inputs, I can literally choose anything I want. The standard way to do this is to choose some values around 0, where 0 is kind of the center. So I'm going to choose -2 all the way up to +2. Why am I choosing those values? Is 1, I can choose any values I want. And 2, I like to choose some values to the left of 0 and to the right of 0, so I get a sense of what the graph looks like on either side of my y-axis. I always like to treat the y-axis as like the center of my graph. So what I'm going to do is I'm literally going to take these values, and my function is 4 times 4 to the x, and I'm going to plug in that -2 and the -1 and so on. I'm going to plug those in where I see x in my function. And my goal then is, using my calculator or mental math, if you feel so inclined, is to figure out for every input what would be my output. So what I would get is outputs of 0.25, 1, 4, 16, and 64. So the key thing here, exponential growth, the key word here is growth. Notice how the values start really small. 0.25 is between 0 and 1. And notice in just a few inputs, I'm all the way up to 64. So my values are growing at a greater rate than they would if this was a linear function. So plotting these points, I'll show this here in red. Plotting these points, I'm going to use just my inputs and outputs. So my first input is -2, and I got an output of 0.25. So 0.25 is going to be about a quarter of the way up. It's just a little bit above 0, and it's between 0 and 1. Then I would have -1 and +1. Okay, then I would have 0 and 4, 1 and 16, and then lastly I have 2 and 64. Now notice my graph goes up to 20. So can I graph 64? The answer there is no. So I'm going to fit what I can, okay? Now the key thing here is, as I started off, you'll notice that this, between the 2 points, All right, it's kind of seemed like it could have been linear, but as we start to go on, you'll see that the gap between these points starts to increase. The gap here between those was 1 box, then I had 3 boxes, and now I have all the way up there. So you'll see that it's starting to increase at a drastic rate. So what happens here is that when I connect these points with my graph, instead of drawing a line, what I'm forced to draw now is a curve. So for an exponential function, we are no longer begin drawing a line, but we're going to be drawing a curve. And notice that this is curving upward because it's exponential growth. Okay, similar example here. I have 3 times 2 to the x. So again, my a value, my initial value here is 3, and my multiplier here is 2. So plugging in my inputs again, I'm going to choose the same inputs of -2 all the way up to +2. Again, what I'm going to do is take those inputs and I'm going to plug them into my function where I see x. Then all I want to do is, using my calculator, I'm going to evaluate each of those for that input so I can then get my outputs. In this case, what I get is 0.75, 1.5, 3, 6, and 12. So you'll notice again, the values are starting off small and increasing all the way up to 12. The idea here is that we're starting at some value. In this case, we're starting with an initial value of 3, and we're seeing that those values are doubling. So what I'm going to do is plot these points on my graph again. So -2 and 0.75, that would be left 2, and then I'm going up 3/4. So I'm going to go up to 0.75, which would be a little bit above 0, but closer to 1 in this case. Then I have -1 and 1.5, which would be halfway between 1 and 2. Again, right now, those 2 points could appear to be linear, but as I start to plot more points, 0, 3, 1, 6, and then 2, 12, you will notice that the spacing between the points gets greater. So if I were to connect these points, you'll see that it starts to grow upwards. The idea, again, in all exponential functions, it's a multiplier. So in this case, you'll notice that between every point that I have 3 times 2 would give me 6, times 2 would give me 12, and the same thing here. So now relating this back to our initial function, we had 3 times 2 to the x. 3, again, is our initial value. So I want you to notice that our initial value is shown right here, smack dab in the middle. So we can see here that my initial value a occurs when x is equal to 0. And then you will see that my multiplier b is just that times 2 that I see going on between my terms. This is what forms that relationship between my initial value and my multiplier, which we see in all exponential functions. All right, next example. We're still going to do some graphing here, folks, but instead I have some changes. So you'll notice here that my a value is now a negative. Okay, so we did talk about that in terms of our b value for all exponential growth functions, that b is going to have to be a number greater than 1. We did also have some restrictions in our last section that b cannot equal any number less than 0, so it can't be negative, as well as b cannot be the number 1. However, a can be a negative. A can be anything. Our initial value can be whatever it wants to be. So in this case, our initial value is -2. And our multiplier is 3. And what we're going to see is what happens when I throw a negative into this for my a value. So again, we're going to graph this the same way. I'm going to plug in my inputs of -2, -1, 0, 1, and 2. My goal then is to take all of those inputs and plug them in where I see x. So again, all of these things here are going to go into my input where I see x. So I would have -2 times 3 to the -2nd power. I would have -2 times 3 to the -1st. -2 times 3 to the 0 power, and lastly, -2 times 3 to the 1st, and -2 times 3 to the 2nd. So my goal, again, is to evaluate each of these functions for those given inputs. So I'm going to get -0.22, that's a rounded number, -0.67, another rounded number, -2, -6, -18. So again, kind of what I talked about on the last slide, you'll see here my initial value of -2 is shown there. And again, between the terms, we have a multiplier of 3 going on. So if I started at that low value, if I multiply by 3 every single time, again, it's going to give me my next value. But the idea here in graphing is, what is it going to look like now that my a value is negative? you'll notice all my outputs are negative. So if I were to plot these, real quick, I just cheated and flipped my graph upside down, but -2 and -0.22 would be left to and down between 0 and -1. I would go -1 and 0.67, which is going to be about 2/3 of the way down. 0, -2, 1, -6, and 2, -18. So in this case, my graph, when I curve it downward, would look something like that. So notice this one. This is a little confusing because we are talking about exponential growth. This is an example of exponential growth, but notice that the graph is going downward. Okay? So this is growth, but what ends up happening here is that you are getting more negative. Okay? So it's like saying you're in debt, right? Your debt could grow, which means, yes, it is growing, but it just means that you're losing more money, right? You're going more into debt. So we can see growth not only in the positives, but we can also see growth in the negatives. Okay, this last example here for graphing, I have 3 times 2 in the exponent. I see x minus 2, and then I have plus 2 at the end. So this one looks a little bit different. Again, we're going to choose our inputs and plot them or plug them in where I see my x value and to get our outputs. So in this case, I'm just going to choose some different inputs. Again, inputs, I can pick whatever I want. So in this case, I'm actually going to go by 2. I'm going to go -2, 0, 2, then I'll go 4 and 6. And my goal is I'm going to take those and plug them in. So this one's a little bit different in how it's written. So I have 3 times 2 to the x. I'm going to start with -2. But then after that, I have -2 and then +2. So a little bit extra sass. Now, I don't want you to worry too much about the function and what it looks like at the moment, but instead what I want you to think about is plugging the things in again and getting the outputs and what our graph looks like in the end. So again, we're going to take that and we're going to plug that in, and I'm going to do the same for all of my other inputs. So I'm going to do the same for 0. I'm going to do the same for +2, and then as well as 4 and 6. And again, what I want to focus on here is more so the inputs and outputs and what the graph looks like in the end. So I'm going to plug all those things in and see what we get for our outputs. So what I should get is 2.185 all the way up to 26. Now these numbers look obviously a little bit different, so let's just see how that looks like on the graph. Starting with our first value of 2.185. So I'm going to go left 2 to -2. 2.185 is going to be between 2 and 3 and a little bit closer to 2. So I'm going to put a point right here. Then I have 2.75. So again, it's going to go left. Oh, sorry, this one's at 0. I'm going to go above 2. 2.75 is going to be between 2 and 3, but this case, it's going to be closer to 3. So right there. Then I would have 5. So I'm going to go 2 up to 5. And then I have 4 and 14. And then the last one I have is 6 and 26. My graph goes to 20, so unfortunately I can't graph that one. So if I were to plot this here, okay, my exponential function is going to look something like that. A little sloppy on that curve, but that's okay. Okay. Now, what happens here is obviously this function looks a little bit different because I have the -2 and the +2. Normally in a regular function, when you see these -2 and +2 at the end, what those are called are transformations. It's going to take these or this graph and it's going to shift it. The -2 is going to shift it to the right, and this +2 is going to shift it up. So you'll notice here that the bottom part of this graph is shifted up to 2. Okay? And it's also going to be shifted to the right 2, so where my initial value would be somewhere around here. Okay, so my whole graph is kind of shifted a little bit, but the idea here, what I want you to see for exponential growth, is the idea of the inputs and outputs and how the outputs are growing at a rate larger than what we would see with a linear function. Okay, this last example, we're going to do the opposite. I'm going to give you guys the graph of the function. We're going to see, can we write the equation of this function? So our goal in the end is let's write the equation y equals a times b to the x. So the best way to do this is, obviously, this is all based upon the points that we have, okay? So from this graph, I'm going to try and identify some points. And to find points, we're going to look at where our curve crosses both an x and a y. So I see a point here at 0, 5. I see a point here at 1, 10. Looks like I have all the way at the top a point of 220. Okay? So, thinking about A and B. So my A value is my initial value. My B value is the multiplier. So I think by the values you can see the 5, 10, 20. So if you look at those values, think of those as my outputs. I have an output of 5, 10, and 20. My inputs are the x values of 0, 1, and 2. So right away, if I look at my outputs, I see 5, 10, 20. I should hopefully recognize the pattern that it's doubling. It's times 2. So I know that my B value in this equation, I'm going to do this in green, is going to be times 2. So it's going to be something times 2 to the x. Now notice I have 5, 10, and 20. So what I wanted you to recognize, and even if I were to choose other points, I would have like 2.5, 1 and 1.25. What I want you to see is that all of those numbers, 5, 10, and 20, are all multiples of 5. What that tells me then is my initial value is going to be the value of 5. So in the end, my equation from this function is going to be 5 times 2 to the x. I start at 5, which is that middle value in my graph, and my values are doubling every single time. Doggy. Doggy. Sorry, folks. My dog's barking. You know what that means, though? I gotta go. So if you got any questions, make sure you jot them down. Shoot me an email. We'll see you next time.